Dear students, welcome. Today we will study implementation and verification of Kirchhoffs Current Law, which is also known as KCL. We will start with the definition and use of KCL, and then we will proceed to example and simulation. Kirchhoffs Current Law or KCL states that the algebraic sum of all current entering and leaving a node must equal to 0. It means that if we have a node, there will be some currents entering the node while other will be leaving it. So when we sum up all the currents entering and leaving the node will be equal to 0. Like that of KVL, Kirchhoff's voltage law, where we had summation of voltages within our loop to be 0. Similarly, here we have sum of currents within a node, that is current entering or leaving the node, equal to 0. This law is used to describe how a charge enters and leaves a wire junction point or node on a wire. Considering the figure below, here we have point A. This red dot is point A. Some currents like I5 and I1 are entering into this point A, while other three currents, that is I2, I3 and I4, are leaving the point A. So, as I mentioned, some currents are incoming to the point A while the other currents are leaving or outgoing from point A. Now we consider that the incoming current, that is I1 and I5, are the entering currents are positive, while we consider that the current leaving or outgoing are negative. So this can be written in the form of equation that I1 plus minus I2 because I2 current is leaving the point A. Similarly, I3 and I4 are also leaving the point A. So we took them negative. So I1 plus minus I2 plus minus I3 plus minus I4 plus I5 is equal to 0. This can be written as I1 plus I5 minus I2 minus I3 minus I4. This can further be written as I1 plus I5 is equal to I2 plus I3 plus I4. Generically, it can be written as incoming or entering currents are equal to leaving or outgoing currents. Its general formula can be written as summation I is the current, summation of currents entering to a node are equal to summation of current that are leaving from the node. Let's take an example and see how it works. Consider the following circuit. Here we have circuit having two voltage sources of 10 volts and 20 volts. There are three resistors, 10 ohm, 20 ohm and 40 ohm. Here we have only two nodes. First node is here and here is second node. You remember what is the element known which is connected among two loops? Branch. This is our branch. Here we have three currents. I1 is entering into the node A, while I2 is also entering into the node A, but I3 is leaving the node. So according to KCL, the summation of currents entering into the node will be equal to summation of current that is leaving the node. That is I1 plus I2 should be equal to I3. So now let's proceed and solve this example. If we cater the loops, then here we have three loops. One is the main loop, without considering the branch. And if we consider the branch, which we have to, then we have two loops, loop 1 and loop 2. The current here is considered in clockwise direction, and here it is considered in anti-clockwise direction. As I already mentioned, the circuit has 3 branches, 2 nodes A and B, and 2 independent loops. Through Kirchhoffs current law, the KCL equation are given as: at node A we have I1 plus I2 is equal to I3, but when we consider node B, then we have I3 is equal to I2 plus I1. Because if we consider this node, then this I3 is entering into the node, while I2 is going out and I1 is also going out of the node. Through the use of Kirchhoff's voltage law, KVL, we can find its equation as: for the first loop, 10 is equal to R1 I1 plus R3 I3 is equal to 10 I1 plus 40 I3. 10 is the value of R1 while 40 is the value of R3. For the loop 2, we have 20 is equal to R2 I2 plus I3 R3. So it can be written as 20 is equal to 20 I2 plus 40 I3. Here 20 is the value of R2 while 40 is the value of R3. The loop 3, which is the main loop, its equation can be written as 10 minus 20 is equal to 10 I1 minus 20 I2. As I3 is the sum of I1 plus I2, so we can rewrite the equation as: for loop 1 we can rewrite it as 10 is equal to 10 I1 plus 40 I1 plus I2. So this will becomes 10 is equal to 50 I1 plus 40 I2. Whereas for loop 2 the equation will be as 20 is equal to 20 I1 plus 40 I1 plus I2. So this will become 20 is equal to 40 I1 plus 60 I2. We now have two simultaneous equations that can be reduced to give us the values of I1 and I2. Now we have to solve the equation of loop 1 and loop 2 simultaneously to get values of currents. We write the equation of loop 1 as I1 is equal to 10 minus 40 I2 divided by 50. Here we separate I1, we take 40 I2 to the left hand side, so it's 10 minus 40 I2 and we divide it by 50. We can substitute the value of I1 in the equation of loop 2, so we will get 20 is equal to 40. Now we place I1 value, that is 10 minus 40 I2 divided by 50 plus 60 I2. Here 20 is equal to 400. We multiply 40 inside with each element. So 400 minus 1600 I2 divided by 50 plus 60 I2. Now we multiply this 50 with each element to cancel its effect. So 1000, 50 multiplied by 20 is equal to 1000. Here 50 will cancel with 50. So 400 minus 1600 I2 will remain, and 50 multiplied by 60 will be 3000. This is actually taking LCM and multiplying the effect of 50. 1000 minus 400 will be equal to 1400 I2. Now we have 600 is equal to 1400 I2, which can be written as I2 is equal to 600 divided by 1400. So we get the value of I2 to be 0.429 ampere. Now putting the value of I2 into I1, we get the value of I1. So I1 will be equal to 10 minus 40 multiplied by 0.429 ampere divided by 50. So we get its value as 10 minus 17.16 divided by 50, which will be equal to minus 7.16 divided by 50. The value of I1 comes out to be minus 0.143 ampere. Now we have to calculate the value of I3. I3 is written in terms of I1 and I2. So we have I3 is equal to I1 plus I2. I3 can be found as 0.143 plus 0.429. So we get the value of I3 is equal to 0.285 ampere. Now we can calculate the voltages as well, as we have the values of I1, I2 and I3. So for R1 we will have I1 R1. For VR2 we will have I2 R2, and that for R3 we will have I3 R3. So this is how we can calculate the voltages. As we are done with the calculations, now let's proceed to our simulator. So we'll go to www.falstad.com/circuit and implement this circuit to view the simulations, whether they comply with the calculations or not. We are here at our falstad simulator. Let's first clear our screen. So we'll go to circuit and check on blank screen. Now let's start building our circuit. Our circuit had 3 resistors, 10 ohms, 20 ohms and 40 ohms, and we had 2 sources of 10 volts and 20 volts respectively. So let's first go to draw, click on the red resistors. We will place 3 resistors here in the same configuration as that we had in our circuit. So this is how we place our 3 resistors. Now we will connect our resistors with the help of wire. So we go to draw and add wire. We will connect our resistors like this. We will extend these 2 wires for the connection of our power supplies or DC sources, DC voltage sources. Now before adding our voltage sources, we have to change the values of resistor. Our first resistor was of 10 ohm, second resistor was of 20 ohms, and the third resistor was of 40 ohms. Now we will connect our DC voltage sources. So we will go to input and sources and click on the 2 terminal voltage source. First we will connect here and change its value to 10 volts, and we will connect the second one here and change its value to 20 volts. Now our circuit is almost complete, except that we haven't added the ground. So we will go and add ground to complete the circuit. Now there are 2 ways to verify the KCL, but before proceeding to verifying KCL, we should define our nodes and meshes. Here is our first mesh and this is our second mesh. Well, this is our node A and this is our node B. At node A, the current I1 and I2 are entering while I3 is leaving, but for node B, I3 is entering and node current I1 and node current I2 are leaving. So as I mentioned, there are 2 ways for verification of KCL. First method is that we go to individual component and check the current drops there, and after that we add those current drops at the respective node, either node B or node A. Or the second method is to place ammeters at the respective nodes and then we check the current drops. Let's proceed with the method 1 first, where we go to individual component and check the current drop there. So we come here at the voltage source 1, where we have current drop of minus 142.857 milliampere, which when converted into amperes, we get exactly 0.142 ampere. The conversion into ampere is very simple. All we need to do is multiplying it with 1000. Now we go to our component 1, that is resistor 1. Here we have current drop of 0.142 milliampere and voltage drop of 0.1429 volts. At the resistor 3 we have 0.285 ampere of current, while voltage drop is 11.429 volts. At resistor 2 we have 0.428 ampere of current and 8.571 of voltage drop. Now if we consider node A and add up our currents here, then we have first I1 is minus 0.142 and I2 is 0.428. When we add them up, we get the current to be exactly equal to 0.285 milliampere. Now we can verify the same readings through pointing out the ammeter at respective points. Let's place the ammeters and see whether we get exactly same amount of currents and KCL is verified or not. For placing the ammeters, we go to draw, output and labels and click on add ammeter. Now we will place our first ammeter here, so we delete this wire and place our ammeter here. You see we have current of minus 142.857 milliampere here, which when convert into amperes we get 0.142 ampere. We will place our second ammeter here, so we delete this wire. So here we have 428.571 milliampere or 0.428 milliampere. Our third current I3 will be here, so we will delete this wire and place our ammeter at this point. Now when we subtract 0.142 from 0.428, we get exactly 0.285 ampere. Hence KCL is verified at this node. Similarly, KCL can be verified at this node as well. So for your home task, you have to verify KCL at all the nodes present in the circuit. You can also find the voltages or voltage drops across each resistor. You can do it so by placing voltmeter across each resistor. This is an additional work in this lab so that you are able to verify the voltages as well. So go to draw and connect the respective points of resistor. So at this resistor you have minus 1.429 volts. At this point we have voltage of minus 0.571. The voltage is in negative because we have to swap the terminals. Now the voltage is 8.57 volts across this resistor, while here at the resistor 3 we are having voltage of 11.429 volts. Now if we try to verify KVL here, we can sum up the voltages. So 10 will be equal to the sum of these two voltages, which is exactly same because 11.429 minus 1.429 equals 10. Similarly here, when we add up these two, 8.571 plus 11.429, we have exactly 20 volts. So this is how you verify KCL, and within the same circuit you can verify KVL as well. This was all about simulations. Now that KCL has been verified through calculation and simulation, now it's time to play your part. It's time for your home task. You have to verify Kirchhoffs current law for the given circuit. You need to do calculations as well as simulation. This is the circuit to which you have to verify Kirchhoffs current law. Here you have two nodes. If you take the above nodes, and you have 4 nodes in total if you take all the nodes. And here you have 3 meshes or 3 loops and only one voltage source. So you need to verify KCL for all the nodes present in this circuit through calculations as well as simulation. This was all about today's lecture. If you have any queries, you can ask. Either you can post it here or email it to me. Best of luck. See you in the next lecture.